Hello, I am Sierra Todd. Kevin Zhang, Bridget Peterson, and I conducted an analysis on the emission spectrum of NGC 6302. So I'm going to begin by discussing planetary nebulae. Planetary nebulae are emission nebulae consisting of an expanding ionized gas shell that has been ejected from a mature red giant. They are formed from an intermediate mass star, typically ranging from 1 to 8 solar masses. They have a very short lifetime compared to the stellar life cycle, which is on the magnitude of tens of thousands of years. Their morphology can be sorted into a handful of categories, but the most common morphology observed are spherical, elliptical, or bipolar. While the Dumbbell Nebula was the first planetary nebula discovered, the planetary nebula we will be discussing today is the Butterfly Nebula. NGC 6302, better known as the Butterfly Nebula, has been observed by the Hubble Space Telescope periodically since May of 1979. NGC 6302 has a bipolar lobe structure, which drives the nebula's characteristic name, the Butterfly Nebula. Its central star is one of the hottest known, with a greater than 200,000 degrees Celsius surface temperature, although it is obscured by a ring of dust and is therefore not directly observable. NGC 6302 is rapidly evolving, making it an excellent target for the Hubble Space Telescope observations over time, as we can track its evolution to learn more about stellar evolution. Hubble Space Telescope instruments, including the Wide Field Camera 3, have been used to observe NGC 6302 in the near-ultraviolet, elliptical, and near-infrared spectra. This panchromatic data has allowed imaging studies to test theories concerning stellar wind observations and shocks, photoionized plasmas, and stellar nucleosynthesis, to name only a few topics. Now, our study differs from this previous experimentation. Using the Butterfly Nebula, the primary objective of our study is to analyze the emission spectrum from the nebula to find whether it aligns with the expected ionized hydrogen spectrum. We are specifically taking a look at the UVA region at 3,730 angstroms, hydrogen alpha at 6,560 angstroms, and doubly ionized oxygen emissions at 5,020 angstroms. We expect that the data will align closely with the ionized hydrogen region, as it is common in ionized planetary nebulae. For our selected emissions, this would mean that we would have peaks with bright hydrogen and oxygen emissions and a less bright UVA region, with reference to the typical ionized hydrogen region emission spectrum pictured below.
And now we present our three datasets. First on the line is our O3 dataset, taken through filter F502N. The N in the filter name designates narrowband filter, which is very selective of the type of light it lets in. This narrowband filter has a wavelength range of typically 3 to 5 nanometers or 30 to 50 angstroms. Here's our H-alpha emission line data. It's taken through filter F656N. And finally is our UVA data taken through filter 373N. Notice in the middle the vertical gap. That's the extinction of UV light from the dust lane around the center of the star. Moving on to our analysis methods, we start by downloading 3 different datasets for NGC 6302 taken at the 3 different wavelengths. We use DS9 to view our data. We align all 3 images with the same rotation and zoom parameters, and we also make sure to use the same scale and color map. Our color map shows NGC 6302 as the blue nebula, with only the hottest gases escaping from the central white dwarf shown in purple. Take notice of the white circle in the middle. That marks the approximate location of the white dwarf, and we measure the width by drawing a line from tip to tip of the nebula and bisecting the white dwarf. We measure the width of both blue and purple regions. Our data is recorded in arcseconds, and we convert it into light years for a real-world measurement. Table 1 presents the width of NGC 6302 measured through the 3 filters. The width of the nebula is displayed in the column titled Diameter 1. Now this is a blue region measured in our color map. The width of the nebula only measuring the hot central gas is displayed in Diameter 2. That is a purple region measured in our color map. The width of the gas coming off the dust lane is also shown. The dust lane's width is longest in the O3 spectrum at 73.3 arcseconds. We are not able to measure the width of the gas from the dust lane in the UVA spectrum due to light from the hot gas undergoing extinction.
Here we converted our three diameters to light years. One can see that the F502N and F656N filters have very similar longest diagonals. These are the doubly ionized oxygen and hydrogen alpha datasets, which we initially predicted would have longer diagonals than the F373N ultraviolet A filter before we began taking our measurements. The dust lanes for both doubly ionized oxygen and hydrogen alpha are considerably shorter than the longest diagonals and central hot gas diagonals. Here is a visual comparative study of our three datasets. One can see that the ultraviolet A image is smaller than the doubly ionized oxygen and hydrogen alpha spectra. The arms of the dataset are more pronounced than in the other two images, and more interior definition can be observed because the ultraviolet A is less intense. The slight difference in length between doubly ionized oxygen and hydrogen alpha can be seen in these images as doubly ionized oxygen has a slightly more intense arm. Note that the dust lanes central to the nebula are only visible in the UVA spectra. Doubly ionized oxygen and hydrogen alpha are both commonly high emission lines for planetary nebula as shown in the emission spectra versus wavelength plot. The doubly ionized oxygen region appears to be slightly more intense than the hydrogen alpha region. This is expected as the doubly ionized oxygen and the hydrogen alpha regions are relatively close in intensity, and the doubly ionized oxygen region appears to be brighter than the typical ionized hydrogen region shown in the graph. The ultraviolet A region is less intense, as expected from the plot, which does not exhibit a peak of a similar magnitude as it does for both other observed spectra. Our analysis has several potential sources of error. One main source of error shared across professional analysis of NGC 6302 is that the location of the central star can only be approximated. We approximated where the central star is by bisecting the dust ring as consistently as possible. As I mentioned earlier, we had about 90% accuracy in our distance calculations when compared to NASA's listed distance conversions. This could be due to an approximated distance to the nebula of 3,392 light-years being slightly off, or because our formula is simplified compared to NASA's formula. The formula we used for our calculations is depicted on the right-hand side. Another potential source of error is that our measurements point to point of the length of the nebula were not always consistent. Each image has its own independent coordinate frame, so we had to do our best visual guess of the same location. Lastly, although minimal, we are using reduced data captured by Wide Field Camera 3. Because Wide Field Camera 3 uses charged coupled devices, the reduction process can cause minimal error. When compared to our other sources of error, however, this error is negligible. Note that our sources of error are highly reduced compared to ground-based telescope data such as that from the Cal Poly Observatory. Thank you for watching. We hope you learned something new about both planetary nebula and NGC 6302, the Butterfly Nebula.